everyone. I'm Norman Wahlberger, and in this video we're going to look at our second famous mathematical problem. It's the Collatz conjecture, or sometimes called the 3n plus 1 problem. It's a famous problem that's been around for quite a while, and it's very elementary. It's very elementary to state, and it's easy to understand what this thing is saying. However, it's a very tricky problem. It's eluded the efforts of all people who have tried it, and many people have had a go at trying to wrestle this thing to the ground. So let's have a look at it. Here's the statement. Is actually quite simple. It's this one. So start with a natural number n. If n is odd, multiply by 3 and add 1 to get 3n plus 1. If n is even, on the other hand, then divide by 2 to get n over 2. The Collatz conjecture is that if we continue this by iterating the same procedure, that eventually we get 1. So no matter what natural number we start with, if we perform this procedure over and over again, if it's odd, we multiply by 3 and add 1. If it's even, we divide by 2. And repeat, eventually we get 1. So the problem is prove or disprove this conjecture. And my estimate for difficulty level is somewhere between 8 and 9 on our scale. This problem has different names. Sometimes it's called the Syracuse problem. It's been called Kakutani's problem because of mathematician Kakutani, who was at Yale, who popularized it in the early 60s. Ulam's problem, the hailstone problem, and perhaps a few other names as well. The conjecture gets its name from a German mathematician, Lothar Collatz, who proposed it in 1937. So let's have some examples of so-called Collatz sequences, or perhaps hailstone sequences. The first natural number that we can start with is the natural number 1, the first natural number. And so then what happens? Well, 1 is odd, so we multiply by 3 and add 1 to get 4. Then 4 is even, so we have to divide by 2. And since 2 is even, we have to divide by 2 again to get back to 1. And then, of course, things repeat because we're back to where we started. So we have to multiply by 3 and add 1, divide by 2, divide by 2, and the sequence keeps on going. There's a cycle now that repeats. This is a very important cycle in this problem. 1, 4, 2, 1, 4, 2, because the conjecture is that if we start with any number n, eventually we reach 1, and then this cycle kicks in and we just go 1, 4, 2, 1, 4, 2, 1, 4, 2. All right, suppose we start with 3. We don't need to worry about 2. We already know what happens with 2. But with 3, the first thing that happens is multiply by 3 and add 1 to get 10. Divide by 2. Multiply by 3 and add 1. And that's a power of 2, so we have to divide by 2, divide by 2, divide by 2, and then we get 1. And at that point we can stop. We know that we're back to this cycle as the conjecture predicts. The next number that we don't know about is 6. We know already what happens to 5 because it's already occurred in the previous list, and also 4. So with 6 it's even, so we have to divide by 2 first. Now we have an odd number, multiply by 3 and add 1 to give 10. And then actually we're in the same situation as we are here. So it's going to be the same, 5, 16, 8, 4, 2, and then we're back to 1. With 7, it's a little bit more complicated. We get 22, then 11, 34, 17, 52, 26, 13, 40, 20, and then 10, and then we know that we're back to this sequence here, 5, 16, 8, 4, 2, and 1. So from now on, we might just do this. We might just describe the sequence up to, say, 10. So a number that we've already obtained before, and then we can dispense with the rest because we know what already happens. So with 8, the sequence is 4, 2, 1, but we've already seen what happens with the 4. So with these very simple numbers, yes, we always do get back to 1. And it's not too hard to check what happens for some other smallish numbers. That pretty quickly we get back to 1. So if we start with 9, then we get 28, 14, 7, and then we'll get back to 1 as we did before. 12, 6, and then that's familiar again. 15, this way we have to go a little bit ways here till we get to 10, and then it repeats. 16 is a power of 2, so the next one is 8, and then 4, 2, 1. So for n equals 27, this is perhaps the most interesting one. For small numbers, it takes 111 steps to reach 1. So with 27, it takes quite a while, and along the way it gets all the way up to 9,232 before it slowly starts coming back down again. So if you were doing 27, at some point you might think, wait a minute, this is not going to go back to 1. This is going to keep on going up and up and up. But it does actually ultimately end up down to 1. For all the numbers less than a billion, this is the number that takes the longest to get to 1. So 670,617,279. It takes 986 steps to get to 1. Which is maybe actually not all that much, considering the size of the number. What evidence do we have for the conjecture? Well, it has been checked by computer up to a pretty big number. So it's been checked true for all starting values n up to 5 times 2 to the 60, which is roughly 5 times 10 to the 18th. That's work of Thomas Oliveira e Silva, and Eric Rosendahl also contributed to that kind of effort. So if there is a counterexample, then it's rather big. And there are really two different ways that a counterexample could arise. There could either be a large new cycle. In other words, a finite list of numbers so that you start at some initial value and eventually you come back to where you started, just like 1, 4, 2. But these numbers would all have to be bigger than 10 to the 18. It would have to be a cycle of very big numbers. Or another possibility is that if we start with a certain value, that we get a sequence which just keeps on growing beyond limit. So that there's no kind of cycle and it just carries on going up and up in some kind of wandering way. So while the conjecture states that neither of these possibilities occurs, it's certainly still a possibility. So it might be that there is such a cycle, but it's way up there, or there is some strange sequence that wanders up to infinity. In fact, there might be lots of such sequences. We just don't know. Over the years, people have considered various variants of the original conjecture. For example, people have looked at sequences starting not with natural numbers, but more generally with integers. Then in that case, there are 5 known cycles. There's the one that we already know. There is the trivial cycle, 0 goes to 0. If you start with 0, you always stay with 0. And then there's -1 goes to -2 goes to -1. So for example, -1 is odd. So if you multiply by 3 and add 1, you get -2. And then that's even, so if you divide by 2, you get -1. So that's another cycle. And then there's a cycle -5 to -14, -7, -20, -10, and -5. And there's one longer cycle that starts and ends with -17. And here it is, I won't go through it, you can read it. That's a cycle also. So there are no other known cycles involving negative numbers, but we don't know if there are some more. There might be others out there too. In this version, the iteration is defined by this. So the n plus first element in the sequence is the nth element divided by 2 if the nth element is even. So we take whatever number we have, and if it's even, we divide by 2. If it's not even, in other words, if it's odd, and it's divisible by 3, then we divide by 3. If it's not even and not divisible by 3, then we send it to 5 times an plus 1. So there's 2 ways of it being reduced. It can either be divided by 2 or by 3. And if not, we multiply by 5 and add 1. And the conjecture is that if you start with any natural number, a0, eventually you get the cycle 1, 6, 3, 1. There's also a 7n plus 1 problem that's somewhat similar, and I'll leave it to you to figure out what that 7n plus 1 problem might be. And I'd like to mention that there's a generalization of this kind of approach due to Keith Matthews called the generalized 3x plus 1 mapping, where there's a bit more number theory involved, but there's quite extensive generalization of different possible variants on the Collatz conjecture. This problem is a very tempting one for a mathematician because it's so simple. The ingredients are so elementary. What we're doing is we're multiplying by 3, we're adding 1, or we're dividing by 2. So only the numbers 1, 2, 3 are really involved. And everything is so simple you have to wonder, how can we not figure out whether there's either a counterexample or find a proof of the conjecture. But many people have tried. Most mathematicians, if you show them a problem like this, they will want to give it a try. And Kakutani used to tell a story that when he introduced this problem to Yale, for the next month, all the mathematicians just worked on this problem. The same thing happened at the University of Chicago. And at some point in the early 60s, there was a joke going around that this conjecture was holding up the progress of mathematical research in America in a significant way. It's very tempting for mathematicians to work on this. But how do we start? What kind of strategies do we have for tackling a problem like this? Well, one very natural thing to do, and I think this probably will occur to most or many mathematicians thinking about this, is to try to convert it to a base 2 problem, or maybe a base 3 problem, or maybe combining them a base 6 problem. So let me remind you a little bit about bases of number systems, and then we'll see how that applies to the Collatz conjecture. So I remind you that when we write a number like 347 in our Hindu Arabic form, that's really short for 3 times 100 plus 4 times 10 plus 7 times 1. Or in terms of powers of 10, 3 times 10 squared plus 4 times 10 to the 1 plus 7 times 10 to the 0. And every number can be expressed as a certain number of 10 to the zeros, a certain number of 10 to the 1s, a certain number of 10 to the 2s, and so on, where the coefficients always range from 0 to 9, the number just 1 less than 10. All right, there's nothing that special about 10, except for the fact that we have 10 fingers on our 2 hands. And we can also represent numbers in different bases. In particular, we can write a number like this in base 2. And what that involves is writing it out in terms of powers of 2, where the coefficients now are just between 0 and 1. Again, going up to 1 less than the base. This is how we actually write 347 as a sum of powers of 2. 1 plus 2 plus 8 plus 16 plus 2 to the 6 is 64, and 2 to the 8th is 256. So if you add those all up, you'll get 347, and that's the only way of representing 347 as a sum of powers of 2 if the coefficients are constrained to be either 0 or 1. So we can represent this sum just like we did this one here in a number, where this 1 represents the fact that we have 1, 1, and then the fact that there's 1, 2 is represented here. The fact that there's 0, 2 squareds is represented by that 0. And then there's 1, 2 cubed, 1, 2 to the 4th, 0, 2 to the 5ths, 1, 2 to the 6th, 0, 2 to the 7ths, and 1, 2 to the 8th. So this is the base 2 representation of 347. All right, so computations in base 2 are just like computations in base 10, except that the addition and multiplication table in base 2 is much simpler than they are for base 10. In particular, 1 plus 1 is now 1, 0, meaning 1 plus 1 is 2, and this is the representation of 2 in base 2. It's 0 1s plus 1, 2. So in other words, we get a carry as soon as we add 1 plus 1, then there's a carry. In the Hindu-Arabic system, we have to get a 10 before there's a carry. Here, a single 2 will give us a carry. So let's illustrate this arithmetic by multiplying 347 by 3. So here's how we would do it. We would write out the base 2 representation of 347. And there's the base 2 representation of 3. And we multiply just the way we do in the Hindu-Arabic system. First we multiply this whole thing by the 1s. So basically just repeat the number. And then we multiply it by the 2s. So that 1 times the whole thing is just copied the whole thing over. But we have to move it over 1 to the right because this is in the 2s place, as opposed to being in the 10s place in the Hindu-Arabic system. And then we have to add these things up, starting from the right. So 1 plus 0 is 1. 1 plus 1 is 2, which is 1, 0. So we write down the 0 and carry the 1. And then 1 plus 1 is again 2, so write down the 0, carry the 1. 1 plus 1, 0, carry a 1. Now we have a 1 and plus 1 plus 1. How much is that? Well, that's 3. And 3 is represented by 1 and carry 1. And then 1 plus 1 is 0, carry 1. 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 And finally, 1 plus 1 is 2, which is 0, carry the 1, and give us 1 there. So that's 347 times 3. And what we get is 1, and then 2 to the 4th. Because that's 2, 2 squared, 2 cubed, that's the 2 to the 4th column. 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, 2 to the 9th, that's 2 to the 10, so it's 2 to the 10. 2 to the 10 is 1024, 2 to the 4th is 16, you add them up, you get 1040, you add one more, you get 1041, which is 347 times 3. Okay, so this is very relevant to the Collatz business, because what do we do in the Collatz game? We basically do 3 things. We either multiply by 3, exactly like this, or we add 1, which of course is very simple. That would just involve taking that 1 and adding 1 to it, which would make that a 0 and make that a 1. Or we divide by 2. Dividing by 2 is very simple in base 2. Because a number is even precisely when its last digit is 0. And in that case, dividing by 2 is just dropping that last 0. Just like dividing by 10 in the Hindu-Arabic system is dropping the 0. If you have 360 divided by 10, that's 36. You just drop the final 0. In the same way, dividing by 2 in base 2 means you just lop off that 0 at the end, and if you like, move all the digits over 1 to the right. Alright, so as I've just said, working in base 2, a number is even precisely when it ends in a 0. So dividing by 2 in that case is just stripping off this 1 and shifting to the right. So let's have a look at this Collatz sequence applied to, say, 347. When we look at doing all the computations in base 2, the advantage of this is that the second operation of dividing by 2 is essentially trivial. We just ignore any zeros on the right-hand side of the number. So really there's only one operation, which is multiplying by 3 and adding 1. So here's 347. And then when we multiplied it by 3, we got something that almost looked like this, but not quite. It actually ended in 0, 1. So what I'm doing now is I'm actually adding 1 to that, because that's what we have to do. We have to multiply by 3 and add 1. When we add the 1 at the end becomes a 0, and the next one becomes a 1. And then that 0 to the right, it just drops off. I'm not even writing it down. So this is actually 521, because it's the 1042 that we got by multiplying by 3 and adding 1 and dividing by 2. Now we can almost do this in one step, and with a little bit of practice you can do this in just one step. So let me see if we can do it here. Let's start with 521 and apply this Collatz map. We're going to multiply by 3 and add 1 and ignore any zeros on the right. So how do we multiply this thing by 3? Well, we've already done that once, so we're going to do the same thing. We have to take this number, we have to shift it 1 to the right, and then we have to add them. But that effectively means that essentially what we're doing is we're taking each position and adding the thing that's there to the thing just to the right of it. That's what effectively we were doing. Of course, we still have to worry about carries. We still have to include any carries that are coming from the previous one. All right, so let's see what we get. Okay, let's start here. When we take this thing and shift it over by 1 and add, okay, the 1 plus the 0 is going to give us a 1. We'll ignore that for a second. And then the 0 and the 1 underneath it will give us a 1. So we're going to get this plus this is equal to 1. Okay, this plus this is equal to 0. So there should be a 0 there. Okay, you might say, well, why is there not a 0 there? Okay, just ignore that for a second. So we really should have 1, 1, 0. Okay, and then 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. 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 1 plus 0 is 1. And 0 plus 1 is 1. Okay, so I have to explain, how did we get this 1 here and what happened to these other things here? Well, the 1 and 0 here are just temporary because we have to add 1 after we've multiplied by 3. And adding 1 turns that end 1 into a 0. There's a carry. That turns that next one into a 0. And then there's a carry. And so we end up with that 1 there. So I'm combining both steps, multiplying by 3 and adding 1, and kind of doing it in my head and getting that. So let's do the same thing for this one here once more. So the 1 and the 0 gives us a 1. There should be a 1 here, but we'll adjust for that temporarily because we're going to add 1 to it. Let's just add 1 to it right now. So that 1 that's there, we're adding 1, so it becomes a 0, and there's a 1 that's raised up there for a carry. Okay, so now when we do this one, there's a 1 plus 1 plus the 1, which makes a total of 3, which is 1, 1. So we write down the 1 and carry the 1. Then 1, 1 plus 1 is 3. Write down 1, carry 1. 0 plus 1 is 1, plus the 1 that's carried is 2. So 0, carry 1. And then this 0 plus 0 is 0, plus the carry 1 is a 1. This plus this is 0, this plus this is 0, this plus this is 1, this plus this is 2, so there's a 0 there and carry a 1. And then this plus this is 1, plus the carry is another 2, so there's a 0 there, and add the 1, and we get this thing here. Alright, so you can see that with a bit of practice, and you can try it on your own, once you do a few examples, it becomes easier. You can check that go from here to here is the next. So what we're doing is we're applying the Collatz business basically just one step at a time. At each step, we're just really doing one operation when we work base 2. So we could call this the Collatz map. Goes from this binary representation to this binary representation. And the numbers are 347, this one's 521, this one's 391, this one's 587, this one's 881. Of course, we haven't finished. This keeps on going. And the claim is that eventually this process ends up with 1. So this is a very attractive setting to work on this problem, because somehow the problem wants us to think in terms of base 2 or base 3 or maybe a combination base 6. Base 6 is interesting because multiplication by 3 and division by 2 are almost the same in base 6. In the same way that, say, in base 10, multiplication by 5 and division by 2 are almost the same. So here's an exercise that you can think about if you're interested in this problem, and perhaps you would like to play around with it and get your hands a little bit wet with it. So think of the Collatz map that we've just talked about as defining something like a dynamical system on the binary strings of arbitrary length. So the Collatz map is something that takes one binary string and outputs a new binary string in a very predictable, clear-cut arithmetical way. And what we're really trying to do is trying to predict the long-term behavior of this map. So one approach to this kind of thing is to study it in a special case or a simpler version. So here's a simpler version. What if we just think about a substring of a number of consecutive ones inside some bigger string? So suppose we start off with a very big number which has a whole bunch of zeros and then a few ones and a whole bunch of zeros, and then there might be some stuff to the left and to the right. I guess it's to the left and to the right. And let's say we're just looking temporarily at this string of ones and what happens to it. So when we start iterating, of course something's happening with these ones and something happening with these ones, but here what we're really doing is just multiplying this by 3. And so the behavior of this triple and how it unfolds is somehow independent of these ones, at least until whatever is here grows big enough to start interacting with what's happening over there. So a kind of preliminary thing would be to try to understand what happens to these kinds of little substrings. And this is actually quite amusing. You can start with some small number of ones and perform this essentially multiplication by 3 map and see if you can predict what happens to that little string inside. So a related question is, what do powers of 3 look like in base 2? That's a sort of arithmetical version of pretty well the same kind of thing. And rather open-ended, is there any possibility of predicting the behavior of this Collatz map or finding rough invariants? In other words, trying to find some kind of things or some kind of numbers or quantities associated with this system that in some way you can sort of predict. For example, if this thing is of size 3 right now, and we look at it after 3 iterations, how big has this little intermediate string gotten? Could it have gotten up to size 20? Well, no, it can't. So there's some definite bound, some kind of invariant that we can say, at least locally, that the behavior is constrained within a certain range. Maybe that kind of thing can help us, maybe not. Okay, it's rather open-ended, so I give this roughly sort of d equals 6 difficulty. You could probably spend quite a lot of time, probably you could spend some years, analyzing how this Collatz map behaves on binary strings. That's basically studying the 3n plus 1 problem. Naturally, one should also think about how this problem looks like in base 3 and probably also in base 6. So the second exercise, can you describe the Collatz sequence or the Collatz mapping that we talked about nicely in base 3 or base 6? The Collatz problem is probably not one that's of earth-shaking importance in terms of its connections with other mathematics. It does connect with some problems in computational theory. So various versions or generalizations of the Collatz problem have been shown to be essentially sort of undecidable. That's sort of interesting. It connects with Post's theory of tags, and that's also pretty interesting. And there's a sort of intrinsic number theoretical aspect to it. In some sense, the way you can think about this problem is that we're also again talking about factorization of numbers. The same prime factorization business that we talked about in the last video in the series is behind the scenes here too. So the whole thing somehow comes down to the relationship between the prime factorization of 3n and the prime factorization of 3n plus 1. This is a very subtle problem of the relationship between the additive and the multiplicative structure. What happens to the prime factorization of a number if we add 1 to it? Clearly all the primes change. There can be no common primes between a number and that number plus 1. But exactly what happens, is there any way of predicting what happens? That's a pretty subtle and an interesting thing that gets connected into all kinds of other mathematical problems. So it's appearing here behind the scenes in this problem too. So there are some additional variants as well. For example, you might look at the numbers 2 and 3 and say, well, all right, can we change those to some other values and leave the essential problem exactly the same? So suppose we agree that if the number is even, we divide by 2, and if the number is odd, we, instead of multiplying by 3 and adding 1, we multiply by 5 and add 1. All right, well, there's one cycle. So next time, can you find any other cycles? Can you investigate this variant and say anything about it? Another possible general strategy with problems like this is to try to convert it into a modular arithmetic problem. So in a very open-ended way, can you find analogs of the Collatz sequences mod a prime, or maybe mod a composite number too? And if we say anything about that, does that reflect anything on the original sequence with natural numbers? So for those of you who have some interest in this problem and perhaps would like to work on it in a little bit more depth, I suggest that you have a look at the work of Geoffrey Ligarius, who's probably the world's foremost authority on this problem. He's written a book called The 3x plus 1 Problem, and inside it has some survey articles. In fact, you can find those survey articles also on the web. And they outline very nicely a lot of the work that has been done on this problem already. So that's a very good starting place if you're serious about trying to tackle this problem, is to find out what other people have already done. And Ligarius is the man to check out for that. So it's a nice problem. It's amusing, it's delightfully simple and tantalizing. And in 100 years, will we know what the answer is? I don't know. In our next video, we're going to look at a problem from antiquity. We're going to go back to the ancient Greeks and to the greatest geometer of all time. He posed a lovely series of problems having to do with circles. So we're going to look at Apollonius's circle construction problems next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.